That is topic of discussion from my side is anti-corrosion properties of metallic substrate via nanocomposite coating. So my name is Dr. Sheerin Masroor, and I have been working as an assistant professor since 7 years in Anugrah Iron College, Patna. So the topic is divided into four sections. Like first is introduction, second is some discussion is there, and next is conclusion and the future prospects. So first I would like to introduce what is corrosion and why we are in need to inhibit its presence. So corrosion is something like it is a degradation of material which is inserted in specific environment, either it is chemically or electrochemical in nature, and which are associated or not associated with any mechanical stress, or technically it can also be called as in related to some kind of tendency by which we can reverse the metal from natural ore state to lower its internal energy. So there are few incidents which have caused a major damage in the history by the corrosion, like some spills in California, some fall of railway traffic lights in England, mislanding of jet stream from the England, and gas explosion of gas pipeline in Mexico, sinking of tanker, and crash of some planes in USA, and definitely as in our country, like Bhopal gas tragedy, which happened to be skipping of some gas, methyl isocyanate, from tankers. So basically, corrosion has been proceeded in a metal if all the component of corrosion cell are present at a time, like anode, cathode, and electrochemical connection in between, and definitely an electrolyte. So picture depicts something steel pipeline which have been immersed in water, and some part of is acting as anode and some is acting as cathode. So at the anodic site, the iron is dissociating into iron 2 plus, leaving the electrons, while at the cathodic site, the water and oxygen are binding together with the electron and forming the hydroxyl line, which these hydroxyl line are further have been taken up by the iron 2 plus ion, forming the iron 2 hydroxide, which is a kind of rust. So this is the basic simplified equation for to form a rust. So there are different methods which have been applied to protect our metallic structures, like there are different design improvement, change of metal, change of environment, potential change. And change of environment is further divided into removal of corrosive constituent, corrosion inhibitor, application of corrosion inhibitor, change of operative parameters, and the next comes coating. Coating have been divided again into inorganic coating and organic coating, coming from the background, coming of the material background, from which background it is coming, either inorganic or organic. So coating are something act as a protective barrier, and they act as a physical barrier which can protect any material from aggressive media from the metal surface. Again, it is of two type, anodic and cathodic. So coating material is anodic when the metal coating is to produce is like iron or steel is protected by coating of zinc, and the process called galvanization. While the cathodic coating is said to be cathodic when the coating material is cathodic in nature to the metal on which the coating is to be produced. And example is iron steel if protected by the tin. So here we are discussing about the nanocomposite coating. So some nanocomposite coating basically consists of two immiscible phases which have been separated by an interface region, and the main component of this coating is like a matrix and the reinforcement material. So the final product with the superior, and by forming these combining these things, we can get a product which is superior in qualities and properties compared to each
Dr.
individual component.
Masroor, sorry to interrupt. We are still can see your slide number 4, few
Oh,
accidents.
which one?
We are,
Oh,
yeah,
okay. So
you
it
have
is
to
not,
change the
it was
slides.
not. Okay, okay, okay. Now it is moving.
Yeah.
So the most important component of the composite coating is the matrix, which either in the form of metals, either in the form of polymer material, or the ceramic nature. So matrix basically binds with the reinforcement material, which transfer the loads in between, and gives a shape to the coating. A large variety of material can be used in matrices. So depending upon the destination, means for what kind of work it has been used. So different coatings can be conditioned, or different coatings can be structured by this. So metal, polymers, and ceramics compete for the anti-corrosion coating on the metal. So they can form a good barrier to protect the metal from the aggressive environments. Again, when we are seeing different thing matrices used for the nanocomposite coating are the metals, polymers, and the ceramics. So for the metals, they are act as a host for various nanofillers, which are significantly improves their corrosion resistance. Corrosion production with nanocomposite metallic coating as a matrices is achieved by building a compact barrier to prevent the charge transfer, which minimizes the permeability of oxygen and iron transportation. So it's the major function of the metal to be active when they are acting as the matrices. So the common metals used for this is zinc, nickel, or cobalt. And it is a common knowledge that zinc can act as sacrificial coating for the ferrous substrate, and the zinc composite provides even superior mechanical properties when they are acting as a sacrificial production against the iron. And they exhibit excellent mechanical barriers, and with a great ability if they are using paints. And the next comes matrices is the polymers. So polymers again, it has been used as a great expansion because they are having easy to produce, they are low in cost, and their weight is almost very not much, they are not much in weight, and they are ductile in nature. So polymers again divided into different two classes, like biopolymers or natural polymers or the synthetic polymers. So for the bio or natural polymers, we are using like lignin, tannin, insulins, extracellular polymeric substance, cellulose, chitosan, and different types of gums have been reportedly using as a matrices in the different nanocomposite coatings. So the basic property of biopolymer coating is that they are easily to functionalize, and we can harvest their best property and exhibit outstanding potential in various differently in biomedical applications. Now, when it comes to synthetic polymers, there are some examples: epoxy materials, polystyrene, polyaniline, polyesters are different substances which have been used as a good corrosion resistant coating, and because they are having excellent scratch hardness, and they are having a good adhesion or strength and wear endurance. So next one is ceramics. Ceramic is a different class of which have been used as matrices, or they are have been employed is an industrial field due to their excellent temperature stability, low density, high hardness, good corrosion, and wear resistant, demanding upon the thermal and mechanical requirements. Now, those were the some matrices which have been used in nanocomposite coating. Now, the next component comes is reinforcement materials or the fillers. So, the main role of the reinforcement material used in the composite material coating is that they have to increase the mechanical and anti-corrosion properties of the system. So, nanofillers depends upon their size, morphology, chemical, functional groups, and their amount present in the coating, and which have significantly influenced the strength of the nanocomposite coating. The dispersion of nanofillers in metallic, ceramic, or polymeric matrix provides a coating with improved characteristics such as hardness, corrosion, and wear resistance, as well as improved thermal stability. Now, the reinforcement material mostly used is the form of nanoparticle, nanotubes, nanowires, nanorods, nano platelets, nanosheets, nanofilms, and nanocapsules. If we are specifically talk about the nanoparticles used as a reinforcement material, so their shapes, their dimension, their surface functional groups have been used as developing enhanced composite coating after incorporation into different matrices. So because of these properties, they have been greatly harvested at different matrices to get desired properties. So but the main difficulties what we are encountering to be used nanoparticles and reinforcement material is that they are high protection efficiency incorporating generally that low degree of particle incorporation in the matrix, as they are very small in size, the agglomeration of the particles of their nanoparticles, and this disturbs the structure or the basic property of the coating. So the smaller the particle size, the higher the agglomeration tendency and difficulty to obtain uniform deposit. So the deposition of the nanocomposite coating is difficult when we are performing our experiment with the nanoparticle. So, beside the conventional materials such as oxide metals and new native or the functionalized nanoparticles such as carbon, graphene, which have been harvested as basic nanoparticles, some organografted nanoparticles also have been used as reinforcement particle in the matrices. So these are different main types of nano size reinforcement material used for the nanocomposite, like what I have disclosed in the previous slide, like nanocluster, nanotubes, nanowires, nanorods, nanoplatelets, and nanocontainers, nanosheets, metal oxide, some metal oxide formulations. Some These are some important nanoparticle used in the composite corrosion resistant coating, which have been reported in some references, where we can easily see that the carbon nanoparticle have been used, the graphene oxide, some metals oxide, organografted nanoparticles, core shell particles have been used as a nanoparticle, and which have been used in particle concentration. These are different concentration on which these nanoparticles have been incorporated. And the basic advantage of this, they are giving the large surface area, high tensile strength, high activity, and high strength, good wear and tear. Wear and tear means they are having a less wear and tear percentage, good mechanical abrasion, and these are some properties which have been achieved when incorporating these kind of nanoparticle. Now there is also some limitation which have been also reported. In synthesis is difficult. They are difficult to handle them, and their process of grafting is also difficult. So these are some kind of means result: metal matrix composite, polymer matrix composites, and ceramic matrix composite. When we are talking about the metal matrix composite, we are seeing from different literature that they are having a superior corrosion resistance and are chemically stable compared to pure metallic coating. When we are producing the metallic matrix coatings and we are comparing the results, corrosion results, with the pure basic metallic coating, then we are getting a good result that they are good in efficiency. For example, the zinc graphene. The picture is depicting a table where we are having a matrix of metal, and these reinforced material are produced, and the substrate, what metal we have protected, is and the process of chemical deposition, how they are deposited over the metal. So we have seen that zinc graphene composite coating is superior over the coating which have been derived only from zinc to protect a metallic
Dr.
structure.
Sheerin, try to wind up.
Okay, so these are two other, like polymer and ceramic matrix nanocomposite. Both are working great as compared to basic polymer, or when they are compared to their inhibition efficiency when compared to polymer and matrix. So now comes this conclusion. To conclude, we can say that nanocomposite coating are high performance material that exhibit unique properties and acquire new characteristic, and then that the individual constituent by themselves, which cannot provide individually. So metals can exhibit new properties that are impossible to obtain at a micro or the macro scale level, which we are getting at nano scale level. By combining a large number of nanomaterial, it is possible to design and create a new composite with improved or new physical properties. And the corrosion control by the corrosion nanocomposite coating involves the preparation and the use of large variety of matrices and reinforced material, which often acts as a synergy with enhanced corrosion and wear properties, and superior mechanical and tribological properties. So developing coatings incorporating the nanotechnology will be a great future, and will give a great impact over our day-to-day life. So in the future, we can see that different smart stimuli responsive or self-healing coatings are expected to arrive for the better corrosion production or giving the better corrosion inhibition efficiency appropriate. And we are looking to synthesize some eco-friendly or anti-corrosion coatings, which can replace the basic coating, which are may toxic to the environment or the human health. And we can arrange a different nanocomposite composite coating with different functionalities, from the simple coatings, which are auto responsive and self healing in nature. So challenges in developing new system to protect a metallic substrate against corrosion include a better understanding of system and complexity and healing mechanism. So this is all for today. Thanks.
On the topic embedment of various types of material in polyaniline matrix for reduction in electromagnetic pollution. Actually, polyaniline is a conducting polymers which have a large number of applications. So where we target to reduce the electromagnetic pollution which is present in nearby us. These are the outline of my present work: introduction, applications of polyaniline, synthesis route, EMI shielding applications, then conclusion and applications. Uh, Now, what is the polyaniline? Polyaniline is a types of conducting polymers. Basically, this is the their monomer contain the benzene ring, but with benzene, here the hydrogen bond is present. Why we use the polyaniline? Because the monomer, their monomer, polyaniline monomer, aniline hydrochloride, it is inexpensive, and the synthesis route of polyaniline is very easy. It have the large stability, environmental stability. It can dope with various types of materials, and it gives high yield after the synthesis, after polymerization, and their electrical conductivity can be varied. So, polyaniline contains can be used for various applications, but out of these applications, we are working on first three applications: EMI shielding, sensor, and supercapacitors. So first figure shows that uh, uh, how we can prepare the polyaniline. Here we use aniline hydrochloride uh, as a monomer, APS ammonium persulfate as a oxidant material. We prepare aqueous solution of these two. After that, they mixing for 24 hours to complete the polymerization reaction. Then we filtrate it, then dry, and then final filtrate. After that, we crush the powder in. So we prepare this powder in a nanocomposite form by using the surfactant CTAL. Here is the another similar process to follow the nanocomposites of polyaniline and graphene. And this is the basic reaction to complete the polymerization for polyaniline pani. And pani is the short form of polyaniline. And these are the vacuum pumps which are used. And these are the samples prepared by us. Firstly, I would like tell one thing. EMI shielding. What is the EM? Just wait. Now, these are the EMI shielding. Here we everybody know surrounding us, lot of electromagnetic radiations are present. It may be microwave, radar wave, visible lights, infrared, UV visible, gamma rays, X rays, all kind of radiations. So but when these radiations come across the any electrical instrument, like you can see the TV, televisions, mobile phones. Sometimes the electromagnetic radiations disturbs the signal. You can see here the one person is drilling in a wall. So sometimes we observe that due to their drilling, a signal of the television is disturbing. Sometimes it may also happen we connect to some another person, but connected to another one person, which is unknown for us. So this is the electromagnetic pollution in the nature. So what we can do? We can reduce this electromagnetic pollution by shielding any electrical equipment, by by our material polyaniline composites. It shield the electronic device. So electromagnetic radiation cannot reach on the instrument. So instrument working cannot be destroyed. So how we can reduce electromagnetic pollution? We can reduce electromagnetic pollution by shielding the material, or it can be stopped. Why electromagnetic shielding? Because electromagnetic shielding is a very important application in the field of medical science, satellites, and army. So uh, it can be, we can understand this. When someone radar send a signal on our aeroplane, so we absorb this signal. We basically radar, how it is work, radar send the signal, and after that, after the interact with the device, it go back and radar detect this signal. But if let us we consider to move another country, we plane will go, their radar will send a signal, our aeroplane absorb their signal will not go back. So in that case, their radar cannot detect our plane, so we can do our, if there is any kind of problem. So this is the main application. So how we can reduce it? So after with the shielding, so how shielding is work? What is the basic need of materials for the shielding application? For the shielding application, shielding types of material, material should be highly conducting material. Either it should be magnetic material. It is because of if the material is highly conducting, so this kind of material will contain the magnet. Conduct in case of conducting material, material exhibit the electric loss. But in case of magnet material is magnetic, there will be magnetic loss. In the magnetic loss, when the incident electromagnetic wave, here we can see incident electromagnetic wave. When it will fall on a material, some part of it reflect, some part of there absorb red color, and only few part will be transmitted. So how the major part is of this, it should be high, it should be absorbed, and some part is reflected. Let us consider if we 100% incident electromagnetic waves fall on a material, so only less than 1% of the incident electromagnetic waves will be across the sample. It is only possible if our sample is magnetic. If the sample will be magnetic, magnetic dipoles will interact the incident electromagnetic wave, and if material is conducting, their electric dipoles will interact the electromagnetic waves. So this is the pellets, rectangular pellets with having the 2 mm thickness. Length is around 23 mm, and their breadth is 10 mm. This is prepared by us. So these are the equations. Now here we can see that SET is the total shielding effectiveness. Shielding effectiveness is measured in decibel units. And for the industrial application, the total shielding effectiveness should be 30 decibels, greater than 30 decibel. Here we can see in this above in C figure, here we can see, here is the sample, here is the sample P1 and V1. Both are having the high, both having the total shielding effectiveness 30 decibel. So what I would like to tell one more thing. In this kind of study, I prepared three types of composites. First is the polyaniline with V2O5. V2O5 material is not a conducting material, not it is a magnetic material. So it is a, but we just study on this material to compare the how magnetic material and conducting material it compare. It is useful for shielding everything. Here we can see the P1 sample is a P1 sample is pure polyaniline. After that, we introduce V2O5 nanoparticles in polyaniline matrix. We can see the shielding effectiveness is decreasing. This is because of, I told, it is not a magnetic material. It is not a magnetic. It is not an electrical conducting material. So shielding effectiveness is decreases. But similarly, kind of investigation is take place in polyaniline and MnO2 nanocomposites material. Here we can see S1, S2, S3, and S4. Almost the total shielding effectiveness is increasing. This is because of we are introducing magnetic MnO2 nanoparticles in the polyaniline matrix. Here we can see the shielding effectiveness is increasing with increasing MnO2 nanocomposites, MnO2 concentration. This is only because of the magnetic character of the material, and that is the magnetic loss is increasing. Here we can see the for all the sample, total shielding effectiveness is greater than 30 decibel. So this material can also be useful for industrial applications. And these are the dielectric measurements, because here we can see if the magnetic character of the material is increasing, their magnetic loss magnetic loss should be increasing. In case of with the increasing doping concentration of conducting material, dielectric loss figure 1 epsilon double prime should be increasing. Now, the main sample of our research. Here, this is the graphene nanocomposites. Here we can see in the figure C, P2 is the pure sample. Here we use C tab as a surfactant. We can see the shielding as the graphene concentration. G1 sample contain 2% graphene, G2 sample contain 4%, then G3 6%, then 8%. Here we can see when we introduce 8% graphene in polyaniline matrix, the shielding effectiveness of the sample is almost 63 decibel, which is a very high for shielding application. Similarly, here we can see here, as I earlier told you, the graphene is a conducting material. Due to the conducting material, the here epsilon double prime. Here we can see epsilon double prime is a dielectric loss. The dielectric loss is increasing. That means the conductivity of the sample is increasing. The conductivity of the sample is increasing. Then the conductivity of sample is increasing. Then the dielectric loss is increasing. So similarly, we also work on MWCNT nanocomposites for polyaniline. Here the similar kind of study. Here we can see the as 2, 4, 6, 8% of doping concentration of carbon nanotube, and graphene. Both are the similar kind of materials. Both are highly conducting materials. So here we can
Dr. Pal, try to wind up in 2 minutes.
Okay, ma'am. Here we can see total shielding effectiveness is increasing. So out of this study, here we can also see dielectric loss. Dielectric loss is increasing. So after these three kind of samples, these are the V2O5 dope, these are the MnO2 sample dope, graphene dope, and a carbon nanotube dope. Here we can see as the V2O5 nanoparticles concentration is increasing, the total shielding effectiveness is decreasing. So we can say that the V2O5 dope sample are not highly useful for particular application, but these nanocomposites we use in sensing application. These give the better results. Now the MnO2 doped samples. Here you can see S1, S2, S3. These are the total shielding effectiveness is increasing. So due to the magnetic character, these samples are also useful. With the increase in graphene concentration, our sample, the total shielding effectiveness is also increasing. And finally, the MWCNT doped polyaniline sample total shielding effectiveness is also increasing. So this is only because of electrical conductivity of graphene, and this is the magnetic character of MnO2 samples. So we can MnO2 doped samples, graphene doped samples, polyaniline sample, and CNT doped sample can be used for industrial applications. And out of on the basis of 3 applications on the low temperature conduction, dielectric property, we published various research papers in very good journals, both on sensing application, supercapacitor application, low temperature charge transport mechanism, and EMI shielding applications. These are our research papers. Thank you, ma'am.
Thank you, Dr. Pal.
So first of all, thank you very much for giving me the opportunity to present my work. My name is Dr. Soma Banerjee. I am assistant professor in the Department of Plastic Technology from Harcourt Butler Technical University, Kanpur. Today's topic for my presentation is recent developments in multi-scale polymer composites, fabrication and associated challenges. So if we can think about the composites, these are quite known material to us. But if we see about the history, the composites are there for the very long time. And we can see that from the era of the Genghis Khan, where the bow has been used, made from composite materials, to the vaulted up house used by the Mississippi period, building wall, etc. To the present days plywood materials, all are made of the composites. So we are in the world of the composites, and specifically here I am talking about the polymer composites. Now, but the definition wise, if you want to just recapitulate that what is a composite. A composite is a material which is having a dispersing phase and dispersion media. In case of a polymer composite, the matrix is specifically made of a polymer, and as the filler or the reinforcement, we are having some material. If it is in the range, the reinforcement, the size of the reinforcement is in the range of the nanometers, then we can say it's the nanocomposites. And if it's in the range of the micron size, then we can call it as the simple composites. With this, we can say that we are in the world of the polymer composites and nanocomposites, where the polymer, these are used in various application areas like solar cell, sensors, actuators, energy generation and storage, and many more. So with this small introduction, I will be specifically coming to my topic for today's presentation, that is the multi-scale polymer composites. As now, what is the definition of a multi-scale polymer composites? The multi-scale polymer composites are those which are having at least two reinforcement, one of which are in the macro scale and another is in the nano scale. So in the pictorial representation, we can see conventional composite will have the matrix material made of the polymer, in which there will be some fibers or some reinforcement, which can be in both in the macro scale or in the nano scale. Whereas in case of multi-scale composites, we will have both two reinforcement, one maybe a fiber in the macro scale and one maybe a nanomaterial in the form of some particles. If you want to take understand this with the help of some examples, then we can say that the multi-scale polymer composites are having nanomaterials or nanofillers like graphene, carbon nanotubes, nano clay, etc., or metal nanoparticles, which are combined with the reinforcing fibers like carbon, natural fibers, glass fibers, etc. So with this, we are now coming to the characteristics of some multi-scale composites. The question is that how the multi-scale composites are, why the people are working on that for nowadays, and why these multi-scale composites are becoming better than the normal conventional composites. The question is that a property of or the characteristics of a composite material will be depending on various factors, like it will be depending upon the size of the filler or the size distribution. That means whether the reinforcement having the nanometric sign or the micron sign. Second thing, whether the filler is, what kind of filler shape is there, whether it is in the form of a particle, whether it is in the form of some whiskers or some fibers form, etc. Then third point is the filler treatment. In the morning, we are having very good, very interesting session about it. So where we can see that the filler treatments can also play a very important role. Like the filler treatment can be some sort of only the physical coating, like stearic acid coating or other coatings, or it can be some chemical bonding, like using the silane coupling agents. As for example, like trimethoxysilane, TMS, etc. So by these two ways, we can make the treatment of the filler, but the main motive is the next point, that is the dispersion or the internal interfacial adhesion about the filler. So we can see that if we are trying to disperse the composite material, if we are trying to disperse the reinforcement inside a matrix, then we want to disperse this very well. And we want to have very good interfacial bonding if we want to improve the properties. So that we can reduce this weak points in our composites. So that will be depending upon the dispersion. Uniform dispersion will be attained very easily if we can do the filler treatment. Next is the loading of the filler. That is also very quite understandable that if we go on increasing the loading of the filler, then there'll be one point will be reaching where we'll be having the maximum optimized property. After that, the property or the will be fall down because of the agglomeration or the aggregation of the filler. And finally, the matrix property and the composition of the filler will definitely have the impact on the characteristics of the composites. Now, in our earlier work, we have worked on the development of a multiscale composites. In this slide, I'm giving you just a view how these are composites are fabricated. The composites are basically, we have taken the carbon fiber where after removing the sizing agent, we have dipped into some coating solution. The coating solution essentially contains the salts of the nickel, and the nickel particles got coated over the surface of the carbon fiber. And then after that coated fiber, we have then using the brush, we have applied the epoxy resin that we have purchased. And after that, we have hot press at a temperature of 60 degrees centigrade for about 8 years to get the polymer composites. Now, we have done various characteristics, and we have observed that in the DMA study, dynamic mechanical thermal analysis, we have found that the storage modulus or the loss modulus, etc., are found to be increasing with increasing the coating time. And from there, we can see that from the graph also we can see that with the coating time, when the coating time is 0, that is we are not coating any nickel particles, then only the fiber and the composites are there. Other than in comparison to that, as a reference material, when we are adding the nickel, we can see that the properties are found to be increasing. The modulus are found to be increasing. We have also studied the flexural strength and the ILSS, interlaminar shear strength of these composite materials. And again, we have observed that the synergistic means some improvement of both when we are adding the multi-scale composites, we can see the improvement is much better. The ACM images has shown that how the particles of nickels have been deposited over the fiber, over the surface of the fibers, and we can see that that up to a certain coating time, we can have the very good properties, like between the range of 15 to 20 minutes of coating time, and after that the properties got down, maybe due to the agglomeration of the particles, which are not adding on any improvement in the properties. So with this note, I'm now coming into the different kinds of fabrications in the multiscale fabrications that can be used for the multiscale polymer composites. Mainly, we have to see about the dispersion and how we can improve the dispersion. Now, the improvement of the dispersion can be done by various techniques, like we have talked about the coating. Other techniques are like we can grow the nanomaterials over the surface of the fiber. We can also spray the solution, spray the solution of the making a solution of the nanoparticles, and then we can spray it over the surface of the fiber. And we can make the electrophoric depositions, or we can graft also onto the surface of the fiber after the treatment of the fiber, so that we can attach the fiber nanomaterial directly into the surface of the fibers. So these are the various approaches by which the multiscale polymer composites can be fabricated. But the main factor which we should focus on is the dispersion, because the dispersion, if the dispersion is not better, then there will no synergistic observation will be observed. So basically, the two approaches are there for the fabrication of multiscale composites. First is the incorporation of the nanomaterial within the matrix, within either the matrix of the fiber, or by impregnation. Means we are having fiber, then we are impregnating the solution nanomaterial with the resin solution. These two approaches are there. but the main focus will be how we can improve the dispersion. The dispersion can be improved by various approaches like ultrasonication or mechanical stirring, ball milling, tools for extrusion, etc. Below, we have shown two more fabrication techniques of the for the fabrications of the multiscale composite. One is the by resin transfer molding, and one is by the compression molding. Compression molding is very common known to us, like we have keep the sheets of the fiber, and between we have impregnated the nanomaterial with the resin, and then we have pressed it over the two platforms, and we can apply the pressure and the temperature, and then it can be cured. In case of epoxy, it can be after the curing time, we can remove it. And when we are applying, when we are adding, by this way, we can do the compression molding, or we can also go for the resin transfer molding. In case of resin transfer molding, there is a resin pot is there, which is actually delivering or transferring a metered amount of the resin in the fiber matrix or our reinforcement, so that there will be less spoilage or splitage will be there, and the distribution will be much better. So these are some examples of the techniques by which we can fabricate the multiscale composites, but each of them having a different advantage and disadvantage. Like solution mixing is the common way we can do. We can also go for the melt process like extrusion and injection molding. These are effective for producing the large scale compounds made with the microscale reinforcement, but this requires some good instrumental facilities. And then compression molding, the common one, mainly used for the transfer thermosetting type of the resins like epoxy, polyesters, etc., which also we can use for the high volume fraction of the reinforcement we can add by these techniques. Other than that, we can also follow the in situ polymerization, where we can actually do both the things, in situ polymerization or in situ particle generation. So instead of in situ particle generation, we are taking the polymer, and then inside that the particles are generating, nanoparticles are generated. Or in case of in situ polymerization, what we can do is that we take the nanomaterial first, impregnate with that inside above the surface of the fiber, and finally we can dip that into some emulsion solution, and we can do the in situ polymerization. Layer by layer is a very common technique which is now emerging nowadays. And finally, the electrospinning. So the most important, one of the most important questions is that why we are going from the conventional to the multiscale polymer composites. Well, the answer is there that we get the synergistic effect very well. We can add on the property or the synergy of both type of the fiber. Like as for example, if I take the case of electrical conductivity, many research have found that
ma'am, sorry to interrupt you. You have 1 minute left.
Sure, ma'am. I just have 2 slides. I have total 14 slides, just 2 slides I have. So if we are talking about the electrical conductivity, just the people are working like for the in the polymer matrix, people are adding the carbon nanotubes. So we know that carbon nanotubes is an electrical conducting filler, but when there is an optimum concentration is needed in order to get the threshold percolation, below which concentration the electrical property will not be get. So if instead of adding that much amount of carbon nanotubes, if we add some amount of conducting carbon black or carbon nanopowders, then we can reduce this amount, and this can reduce the percolation threshold to the minimum value of the conducting filler. So by this way, we can tune various properties like mechanical strength, like electrical conductivity, like thermal conductivity, stability, etc., where we can add on both the properties. And these are some of the examples of where the multiscale polymer composites are used nowadays. The main, all the details can be found in our recent publications, and we can see that is everywhere. And it's starting from the energy sector to the defense military to the packaging, everywhere we can see the applications. So in the conclusion, what I want to conclude is that the multiscale polycomposites have opened up a new era for the development of the new generation polymer composites, because the fabrication definitely plays an important role, and because of the dispersion efficiency, because of the interfacial bonding, improvement, etc. So the fabrication plays an important role. And if we can optimize all the factors like I have discussed, that loading, the treatment, and the dispersion, etc., treatment, etc., then we can optimize the property and we can utilize the benefit of both the reinforcement both in the micron scale and also in the nano scale. So effectively, which will definitely synergize the properties of the composite. With this, I want to thank the session chairs for giving me the opportunity and the organizers. And thank you very much. Any question, I'll be happy to answer.
Mechanical strength and durability properties of LC3 concrete incorporating titanium dioxide and lathe fibers. My paper ID is 197. These are the contents of my presentation, which I'll be going through in the next few minutes. As everyone of us know that concrete is a versatile material and it is the widely used material, and cement is the main contributor across the globe in concrete. Therefore, as the world shifts towards more sustainable practices, there is a growing need for alternative construction materials that are not only environmental friendly, but also economically viable. Therefore, LC3, that is lime calcined clay cement concrete, is a novel cementitious material and offers an eco-friendly and cost-effective alternative to traditional cement concrete. So this innovative blend significantly reduces the environmental environmental footprint associated with traditional Portland cement production. Therefore, the LC3 is a low carbon option. Next, the scope of the project. The main scope is to replace the cement using lime calcined clay and also addition of titanium dioxide and lathe fibers on the strength, durability, and microstructural properties of LC3 concrete. Where in this project, the LC3 is replaced with 40% of cement by weight. And the study is done on M30 grade of concrete with lime 15%, calcined clay 25%, and cement 60%. Therefore, the study is experimental oriented. Coming to the next, the materials and methodology. The materials used are as per the IS code, IS 383-1970. So we have used calcined clay, lime powder, lathe fibers, titanium dioxide. Calcined clay, lime powder, lathe fibers are obtained from the local industries. Calcined clay is light pinkish gray color. Lime powder is procured locally. Lathe fibers are with aspect ratio 5:20. Titanium dioxide, which is a nano material, it is used to reducing staining and discoloration, and it also improves the performance, longevity, and aesthetic qualities. Also, we have cement, fine aggregate, coarse aggregate, and water, and the basic properties of these materials have been tested and are well within the specific guidelines. Yes, coming to the methodology, this is the methodology which I have used in the study. Material procurement, testing of the materials, concrete mix design. And when it comes to concrete mix design, the proportion is 1 is to 2.07 is to 3.59 with the water cement ratio of 0.43. The mix design is done for M30 grade of concrete and is carried out as per the codal provisions of IS 10262-2019. After the mix design is done, casting of specimen is taken up, and then testing of specimens, where the test under strength criteria, durability criteria, and microstructural studies have been done, followed by results and discussion and conclusions. Coming to the testing of materials, yes, the different mixes. As you can see in the right corner, the table, we have different mixes which are taken up. NM is the normal mix, which is considered where 100% cement, calcined clay is 0%, lime is 0%, and then LC is nothing but your LC3 concrete, LC mixes, which have different combinations varying from 70% to 20%, and the calcined clay as well as lime. So here, based on these combinations, the standard consistency, initial and final setting time test results have been calculated, and compressive strength results also have been calculated, and it is found that LC2 mix gives us a better result, which keeps the a well balance between the materials. Therefore, in the further experimental results, LC2 mix is being considered, and the final mix combinations with cement 60%, calcined clay 25%, and lime 15% will be considered for the further analysis. So based on that, we have different mixes. That is the normal mix. This is the LC3 mix, LC3 mix with nanomaterial, LC3 mix with fibers, LC3 mix with nanomaterial and fibers. So these are the combinations which have been used to produce the different LC3 concretes. Coming to the next one, the different tests conducted as per the code IS 516 is that strength test, compression, split tensile and flexural strength test. Durability, we have water absorption, water sorptivity, rapid chloride penetration and water permeability test. And microstructural studies scanning SEM, XRD and FTIR. So coming to the next part, it is the optimum dosage of LC3. So here, based on the compressive strength result and the different mixes, we can observe that the compressive strength obtained for different mixes are presented, and the normal mix, that is M1, gives us a compressive strength of 40.15, whereas from M2 to M7, which is the LC3 trial mixes, in this M3, which is LC2, gives us 36.15 Newton per mm square, which is highest amongst the other mixes. So this is the combination which is taken up based on the compressive strength, standard consistency, initial setting time, and final setting time. So this mix has been considered for further analysis. Next, coming to the experimental results, first the strength test. Here, I am going to show you the results of the compressive strength. So this graph indicates the results of the compressive strength for different concrete specimens. Here, it is clear that the strength of normal mix is and LCNF mix is higher compared to the other mixes. The most important thing is the LCNF and NM have similar strengths. The addition of TiO2 and lathe fibers in LCNF has compensated for the potential reduction in strength due to inclusion of calcined clay and lime. The LCNF mix has a well-balanced composition of calcined clay, lime, fibers, and titanium dioxide, which collectively enhances the strength. The same thing is observed for the split tensile strength, where the nominal mix is 1.95 and LCNF mix is 2.13. And finally, the flexural strength, the nominal mix is 4.53 and the LCNF mix is 4.53 compared to other mixes. It tells us that the synergetic effect of these components in LCNF leads to higher strength among the mixes. So the trend normally in the according to the strength test is the same compared to compressive, split tensile, and flexural. Coming to the durability test, the first one is water absorption test. The reference mix has a moderate water absorption rate of 5.22, and with respect to this, the LC mix exhibits a higher water absorption rate, which indicates that the introduction of calcined clay and lime has increased and slightly decreases in mix LCN as well as mix LCF. LCNF shows significantly lower water absorption, which is notably better than the other mixes. The addition of titanium dioxide and lathe fibers in LCNF makes the concrete more compact and results in enhancing the concrete's performance to absorb less water. Coming to sorptivity test, the level of water on the surface. Again, here we can compare the nominal mix as well as the LCNF mix. The trend is almost same when it is seen with respect to water absorption, but it slightly increases for LCN, where it is LC3 concrete with nanomaterial because of the porous nature of concrete. Then we have the water permeability test. It is observed that the LC3 concrete also falls within the acceptable range for water penetration depth. The water penetration depth, the standard depth is around 25 mm, whereas all the results are within 25 mm, and nominal mix of gives us a penetration depth of 20, whereas LCNF also gives us the depth of 20, and therefore we can say that the LCNF demonstrates a strong resistance to water penetration with a depth of 20 mm, measuring that comfortably meets the acceptable limits. And finally, RCPT test, that is the rapid chloride penetration test. Here, when we compare, the chloride penetration is decreasing when LC3 concrete specimens are taken into consideration compared to the normal mix. And when it comes to LCNF, right, it is more resistance towards the chloride penetration compared to the normal mix. So LCNF demonstrates normally with the addition of nanomaterial and lathe fibers in LC3 concrete offers excellent resistance to chloride penetration. Yeah, here I have the graphs related to all the mixes with respect to scanning electron microscopy. So SEM images shows the interaction of different materials and its reaction with each other. So here the unreacted samples, reacted samples, CHS gels, pores, cracks, lathe fibers, nanomaterials, all of them are indicated in the form of image through scanning through the microscope. And this indicates the proper mixture of the materials. Coming to the next result under microstructural studies is the X-ray diffraction results. So here the 5 graphs are indicated with respect to all the mixes, that is normal mix, LC3 mix, LC3 with nanomaterial, LC3 with fibers, and LC3 with nanomaterial and fiber mix. So XRD patterns of all the mixes reveals the presence mainly of amorphous, semi-crystalline and crystalline phases, which is noticeable from the peaks of 20 theta and 40 theta. So this is the range where we can observe that the peaks are common in all the mixes, right? So XRD pattern of normal mix indicates that it has coesite, corzite, titanium oxide. Then LC mix has clinohyperstein, silicon oxide, quartz. LCN mix has diphosphide anorthite. Then LCF mix has quartz, magnesium, zinc, rutile, and LCNF mix is going to have moissanite, titanium oxide, rutile, quartz, magnesium, calcine. So all this indicate the peaks exhibiting the highest intensity suggest the dominance of the crystalline phases, whereas conversely, the peaks falling between 40 theta and 100 theta displays the lower intensities, indicating an amorphous as well as the non-crystalline state. Coming to the FTIR results for all the mixes, the FTIR results for the first 4 mixes, that is normal mix, LC mix, LCN mix, and LCF mix, have the same trend. These wave numbers and associated bonds represents various functional groups or compounds present in the mixes, including carbon-hydrogen bond, carbon-oxygen bond, nitrogen-rich compound bonds, then carbon-carbon double bonds, nitrogen triple bonds, silicon-oxygen bonds. So when it comes to LCNF mix, there is a lot of variation because of many materials present into that, right? And this is where we can compare LCNF mix with the other mixes. Coming to the conclusions, yes, amongst the LC3 mixes, LC2 mix exhibits the highest strength due to its well-balanced composition of cement, calcined clay, and lime. Coming to the strength test results, compressive, split tensile, and fractional strength of LCNF mix with its balanced combination of calcined clay, lime, lathe fibers, and titanium dioxide has been effectively enhanced to a level comparable to the normal mix. The third conclusion, that is the LCNF mix significantly reduces water absorption and shows balanced sorptivity value, making it more impermeable and outperforming the other mixes, while the presence of calcined clay and lime in the LC mix contributes to higher water absorption. Then the LC3 concrete exhibits superior resistance to chloride penetration, ensuring durability in various applications and making it a promising choice for structures in corrosive environments. Finally, the water penetration depth measurements for the concrete mixes indicate that LCNF and LCN exhibits the strong resistance to the different mixes. So, and they are found well within the acceptable.
Okay, a very good evening to one and all present here. Myself, Dr.Reena Bakale, Assistant Professor in Department of Physics, Amravati University from Varud. Now here we are presenting my small part of research, and that is the relaxation behavior of polymer thin film. Now in this paper, we have to make a thin film of 2 composite polymers. Now here we have to use the polymer, that is PVC and PMMA, and we have to use the 2 dopant, that is iodine and cinnamic acid, and make a thin film by using the isothermal evaporation technique. And And if once you prepared the film, then applying or try to calculate the relaxation time on the basis of current time characteristics. As all of you know that the basic principle of relaxation time is that the system stability is possible only when the relaxation time is shorter than mean time between the two disturbance or two polymers. Here, that's why we have to use here the two polymer or blending of two polymer. And the polymer relaxation is nothing but the time referred to the speed at which the polymers reaches to the equilibrium after an external force has been applied. Now that's on that basis we have to prepare this two film and make the selection criteria for the two polymer, that is PVC and PMMA. And this two polymer we have to select on the criteria, that is the proton donor and proton acceptor criteria. And we have to measure the current time characteristics by applying the direct and reverse polarity. And on that basis, we have to calculate their relaxation time and some other parameter, that is drift velocity, density, that is charge carrier mobility. That's all these parameters we have to try to calculate from that film. And the basic keywords of the paper is that this we have to use again the two polymer PVC and PMMA, and we have to make the composition of the two polymer and calculate the relaxation time. And here we have to make the improvement. A polyblend improves the cost performance ratio. As all of you know that all are working on the polymers. That's why the basic thing all are known. And here we have to make the thin film, making the ratio. They have not equal ratio, not equal ratio of equal amount of PVC and PMMA. Here we have to mix these two polymer on a particular ratio. Here we have to use the ratio 3:1 and adding a dopant in a percentage 0.24. 0.6, 0.8 and 0.1, and both the polymer we have to dissolve in a universal solvent, that is tetrahydrofluorant we have to use for the mixing of these two polymer, and make a thin film by using the isothermal evaporation technique. Here the selection criteria, again we have to show that this is the selection criteria of our research, and make a thin film. You have to make this thin film. This is the pool of mercury. We have to pour this mixture on this pool of mercury, and this is a sample film. We have to make during this investigation, we have to measure their thickness on the basis of the microscope in the conjugate and the fine thin film we have to prepare, and this having the thickness is about 18 micrometer. And then the next part, we have to calculate the relaxation time. The first of all, we have to calculate the current time characteristics. And here we have to see in this two picture, there is in these two figure. First figure is of the iodine dope sample, and the second figure is of the ceramic dope sample. And in both the figure, we have to take the two graphs of each dopant material. One is for direct polarity and one is for reverse polarity. On that basis, we have to calculate their relaxation time. And these are the other parameter that we have to calculate, that is mobility and the charge carrier and the density. All these parameters we have to calculate on this basis by using this certain formulas we have to use. Here for relaxation time, we have to use this twice and relaxation time, and this is the formula. On that formula, we have to calculate the relaxation time. And this is the electric field strength. For each concentration, we have to calculate the values of the drift velocity and the current density value for each sample dopant, that is cinnamic acid and iodine dope. The basic principle or the basic aim of this work is that, as you know, that there are two polymer, mixing of two polymer, and the polymethyl methacrylate is one of the best polymer that having the relaxation time is good, and we have to calculate this relaxation time, and we have to try this with another polymer, that is PVC. And conclusion, finally we have to conclude that the polymer has a wide set of relaxation time that confirms the regrouping of the chain unit and the chain region. The relaxation time determined, the empirical formalization should be regarded as the average relaxation time, and this relaxation in the polymer involves a large number of stimulus process proceeding at the different value, that is at the different relaxation time. And this is the references that we have to use during this investigation. And this is, thank you.